The math says the mathematics says both, but reality says one. The Schrödinger equation. This is the core mathematical equation of quantum mechanics. It is deterministic, meaning if you know the starting condition, you can perfectly calculate the future. And linear, meaning it allows for superpositions. It states where a particle is in a multiple places or has multiple properties at once. The conflict here, the equation tells scientists that the particle should exist in multiple states at the same time. This is a proposition. However, when we actually go look at the particle, measure it, we only ever see one single concrete outcome. We never see a particle that is both up and down at the same time. The Copenhagen interpretation. To solve this contradiction, Niels Bohr and his colleague created the Copenhagen interpretation. They did not try to change the math. Instead, they added a new rule called the collapse postulate. The rule, they declared that as soon as you measure a quantum system, the wave function suddenly collapses. What that means, uh, the magic math that made the particle exist in two places at once stops working, and the particle is forced to randomly pick just one outcome. The other possible outcomes simply vanish. We have a fatal flaw here. The criticism. The Schrödinger equation is smooth and continuous. The collapse is sudden, abrupt, and discontinuous. Crucially, the collapse cannot be mathematically derived from the Schrödinger equations. You cannot use the equation to predict when or how the collapse happens. It is an arbitrary external rule that physicists had to glue onto the side of the equation to make the math match reality. The bigger picture, this text is likely setting up an argument for an alternative interpretation of quantum mechanics, like the many worlds interpretation. Instead of adding a magical collapse rule, which is the text calls a tack-on, the many worlds interpretation argues that no collapse happens. Instead, the universe branches. In one branch, the particle goes up, and in the other branch, it goes down. So in that interpretation, the Schrödinger equation can stay mathematically pure and deterministic without needing this artificial collapse rule.